Okay, thank you, Professor. Good morning to everyone. My name is Davide Saguatti. My tutor is Professor Giovanni Verzellesi. My talk today is Semiconductor Devices and Technologies for Electronic and Optoelectronic Applications. I'm going to talk about two different types of devices. The first one is a current-assisted photonic demodulator for time-of-flight-based CMOS 3D image sensor. The second one is high electron mobility transistors based on indium phosphide, on which have been implemented the field plated to be used for high voltage, high efficiency RF applications. The current assisted photonic demodulator is a photodetector based on silicon, which has got two modulation electrodes, and thanks to these electrodes you can apply modulation voltage, which will create majority hole current into the substrate, and so photo-generated electrons can be detected and collected at one side or the other depending on the polarization direction of this modulation voltage. Several studies have been carried out. One is related to the charge transfer efficiency of this device, which is the capability of this device to collect electrons at one side or the other depending on the bias voltage. On the left you can see the experimental results and the simulation about the collection currents, and on the left the charge transfer efficiency. This device can offer 0.8 charge transfer efficiency at 0.5 volts bias. About frequency behavior, we simulated and studied the contrast, which is the ratio between the AC component and the DC component of the collection current. Both experimental results and simulation shows 3 dB bandwidth higher than 45 megahertz. We studied also the Electron Geometry, actually the modulation Electron Geometry. As you can see from the third picture, if you design and fabricate electrodes as a U shape around the collection electrode, at a defined power consumption, you can get a higher charge transfer efficiency thanks to the more efficient electric field which is generated by the two modulation electrodes. This is a photograph of the fabricated chip. Thanks to the intrinsic demodulation capability of this device, which is the capability of detect a phase difference between sent and the received signal. This device is really interested to be used in a time-of-flight 3D camera, which is a three-dimensional camera, which can get the information distance, converting it from the phase difference gotten from the sent sine wave and the received sine wave. Both linearity and phase errors are pretty good. I'm moving now to the second device, which is a high electron mobility transistor. HEMTs are field effect transistor built using different band gas materials. In this way, you can confine electrons in a two-dimensional quantum well, and exploiting the really high mobility that, for example, in this case, indium gallium arsenide and other 3,5 compound semiconductor can offer as compared to silicon. Actually, these devices are one of the alternatives for the next sub-22 nanometers electronics roadmap. We implemented the field plate technologies on this device, which is extension of the gate metallization to the drain side of the device. And thanks to this extension, the electric field under the drain side of the gate edge can be reduced, and in this way you can improve the breakdown voltage. The trade-off of this is the increasing in the gate capacitance. So, of course, the FT and Fmax will be affected, and the frequency behavior will worsen. Thanks to the improvement of the breakdown voltage up to 20-30 volt, you can use these devices for high efficiency power amplifiers, LNAs, and transceivers. Here you can see simulation and experimental results about breakdown voltage, which can be increased up to 19 volts as compared to 3, 4 for the standard device. and the frequency performance, which shows 35–50% worsening with respect to the non-field plated device. But the interesting point is that this effect can be overcome if the bias is up to, for example, 9 volts, is a high bias. This is my funding projects and publication. Thank you for your attention.